Welcome back to Advent of Code 2023. We're just about to begin. Got 1.5 minutes. So on problem 17. Okay, just wait for this to start then. Yesterday, what did we have yesterday again? Oh yeah, not too hard. Tricky to code, but, well, no, tricky to write it out, but not really tricky to code. Got a little lava animation here. Okay. We are, so day 17, so like 8 days left. I mean, usually the most difficult problems arrive about, I don't know, 15 onwards. But it still varies, but 17. Go, go, go! Clumsy crucible. The lava starts... Oh, we've got more 2D grids, okay. The lava starts flowing rapidly once the lava production facility is operational. As you leave, the reindeer offers you a parachute, allowing you to quickly reach Gear Island. As you descend, your bird's eye view of Gear Island reveals why you had trouble finding anyone on your way up. Half of Gear Island is empty. But the half below you is a giant factory city. You land near the gradually filling pool of lava at the base of your new lava fall. Lava ducts will eventually carry the lava throughout the city, but to make use of it immediately, elves are loading it into large crucibles on wheels. What is a crucible? It's like a bowl. Alright. The crucibles are top-heavy and pushed by hand. Unfortunately, the crucibles become very difficult to steer at high speeds, and so it can be hard to go in a straight line for very long. To get Desert Island the machine parts it needs as soon as possible, you'll need to find the best way to get the crucible from the lava pool to the machine parts factory. To do this, you need to minimize heat loss while choosing a route that doesn't require the crucible to go in a straight line for too long. Fortunately, the elves here have a map that uses traffic patterns, ambient temperature, and hundreds of other parameters to calculate exactly how much heat loss can be expected for a crucible. So it's kind of like a searching algorithm, but you've also got to watch out for chains. Well, let's read on. Each city block is marked by a single digit that represents the amount of heat loss if the crucible enters that block. The starting point, the lava pool, is the top left city block. The destination, the machine parts factory, is the bottom right city block. Unless you leave that block and return to it, which you can do, and it may be valid to do. It may be valid to return to locations. Okay. Because it is difficult to keep the top-heavy crucible going in a straight line for very long, it can move at most 3 blocks in a single direction before it must turn 90 degrees left or right. The crucible also can't reverse direction. After entering each city block, it may only turn left, continue straight, or turn right. I sort of see what to do, but it's several things we need to account for. Alright, this path never moves more than 3 consecutive blocks in the same direction and incurs a heat loss of only 102. So we can spiral, or we can turn around, we can visit past locations again. Okay. So it's basically breadth first search. Well, not quite. We're minimizing heat loss. We can treat heat loss as distance. So we're trying to find a minimum distance path that may revisit nodes, satisfying these constraints. Man, okay. All right. If we code this correctly, it shouldn't be hard. We just gotta make sure we code it correctly. So, distance to a cell is just, well, basically it's the heat, the value of that cell, okay. And these go up to 9. Alright. Let's say grid equal. You know what? We should copy the pause thing. That was useful. Okay. Grid equals. Let's fetch the input first. Just deal with that. All right. So grid equals empty list, or so we want. Is this again? Just this whole thing. One for one again. They love doing their 1-for-1s, don't they? Are all these islands? Oh, I think they're implying that all the islands are 1-for-1 by 1-for-1 or something. Okay, so no, this was just a city within the island. Hello, Hereford Bull 17. So this. Okay, so we've got the grid. Start equals pause 0, 0. How's this problem looking? Not too bad. I mean, it's textbooky. It's basically find a minimum path where these are basically the distances to enter a cell. It's heat loss, but you can think of it as distance, so trying to find a minimum path through this. But there are constraints, which we can also quantify. We're not allowed to go more than 3 moves in one direction in a row. So our state, okay, we have to think about what a state is. State will be our location, the direction we're facing. No. Yes, the direction we're facing. The number of cells we've previously been to within that chain. Yeah, those 3 parameters, basically. You're allowed to revisit cells. Okay. So the runtime will basically be like the the number of cells multiplied by 3, because you can have 3 different chains, 0, 1, 2, or 3 for your chain lengths. And then that multiplied by 4 directions you could be facing. So it's fine. You can run that. Goal equals pause. So it's going to be n-1, m-1. Define BFS. So BFS is going to find the minimum heat. Start. All right, so a state. All right, it would just be a tuple. Start state equals, it's going to be a tuple with, oh, you know what? We don't have a direction to begin with. Do we? So we just don't have a direction to begin with. That's fine, we can just put a none in there. It's a bit weird, but it's just that one case where there's none. Fine, we can make that one exception. But okay, so direction is going to be none, and then the chain is so we want this to mean the number. The current length of the chain, so it's going to be 1. Yeah. Okay. Let's make a note here. Position, direction, chain length. So the start state is that, the goal pause is that. So BFS, we have a start state. And a goal pause. So we're gonna need from Q import. Could do a star search, shall we? What is the minimum? It's 1, so it's basically Manhattan distance would be the heuristic. That, yeah, let's try to make it efficient. Import, we use a priority queue. We have to use a priority queue anyway, because it's Dijkstra we're doing, not BFS. In fact, we'll make it A star. So, heuristic. For a given state. Let's just say it's the Manhattan distance, so we need to define distance. So it's going to be abs of self.row minus other.row plus abs self.column minus other.column. Return so heuristic is an estimate from S to the goal. So it's going to be s.dist goal pos. That's our heuristic. Alright, so I'm coding A star. I could just copy in A star from before, but I think it's instructive to just write it from scratch every time. So, how do we get started? We have a queue. Alright. We have a distance table. Those two things. Anything else? Any other data structures we need to maintain? We don't need to return the path, do we? No, we just need the actual distance. Okay. So we don't need a came from map. Okay. Distance. We can say start state to 0. Q.put start state. But we need the tuple, and that's going to be the f f distance, which means the distance to start state plus the heuristic. So that this is actually, it's just going to be h of the start state and the start state itself. Also, heuristic should use a state because there's other parameters in the state which could matter for the heuristic. We're ignoring those. So, but we should say it's going to be S0. Call it state. Okay. This... Okay, I'm already overwhelmed with the stuff here. So that's how we get started, right? Then we have the main loop, while not q.empty. So we're gonna pull out current equals q.pop. No. q.get. That gets the lowest priority, it gets the lowest priority item currently in the queue. So that's the one with the lowest projected. Shortest path to that point plus projected distance to the goal. Okay. Now, if okay, because we're doing lazy deletion here. So when you put something in the queue with a given priority, you may later find a different path to that same state, which is a shorter path. You then put that in the queue. The old state is still in the queue, is still floating about in there. The shortest path one is going to be the next one to be pulled off the queue. But the one with the kind of inefficient path is still in the queue. So we need to do lazy deletion here. We need to say fdist current equals q.get if fdist is worse than what we currently know is the best dist for that state plus the projected distance for that state. That means we've already processed the better one because it would have come out earlier. Right? So we skip this. This is lazy deletion, I guess. Hope this is right. Let's also make these a bit more explicit. Current state. See, I could have just pasted in my whole A-star algorithm from before, and that would have got me to the solution faster. But it really helps to reason this through. It just helps you memorize this. Okay, so yeah, if okay, that's lazy deletion. All right, so otherwise we're looking at the best path to this current state. Well, so let's make this completely explicit. We're actually putting in dist start state plus, but that's 0. But I want to write it like that, just because it kind of makes it completely clear why we're doing that. Yeah. Okay. All right. The other big method we need is the get neighbors state. The get neighbors method. We should probably put that up here. Fine. Get neighbors from state. This is the other. This is probably the trickiest part. So basically, we can go anywhere but backwards. They said. Yeah, they said anywhere but backwards. So if the chain length is already 3, we can't go forwards either. So we remove backwards. So we just kind of iterate over all directions, but we discard backwards. And if let me have a think. Okay, let's do it like this. Let's say for DI DJ in so it's going to be pause 1 0. So these are the 4 cardinal directions. In no specific order. We're gonna need a minus, I think. In fact, we're going to need negation as well. Maybe not. And what am I trying to do here? So we want to discard skip backwards. Which one is backwards? Backwards is going to be the one that is the negative. Is it? Is that? Is it neg? So we would just do return row equals negative self row, column equals negative self col. So for delta, why am I doing DI/DJ? Okay, for delta amongst those 4 different directions, if delta, okay, let's unpack the state here. We've got a pause, we've got a direction, and we've got chain length. equals state, right? So for delta, if delta equals negative direction, you could also add them and check if it's 0, but then you have to compare with pos 0, 0. Skip that one. If delta is direction forwards and chain length is already 3, that means we've gone 3 in a row, skip that one. So we've now got all the valid directions we're allowed to turn. So new pos equals pos plus delta. All right. New direction will be the delta. New direction equals delta. If new direction is not equal to the old direction, hang on. I think we're skipping steps here. No. Okay. We don't want to... Okay, turning is a move. Because we need to process the location where you turn. You turn on the spot. So you would never turn fully around. You would never turn right, then turn right. Hang on. But no, that would mean going backwards, wouldn't it? So you're not allowed to do that. So you do have to turn and move in one go. It has to be an atomic operation. You can't just turn left on the spot, then turn left on the spot. Okay, we're fine as is then. I was thinking we want to make turning a move and going forward a move, but that's bad because then it'll allow us to go backwards. So we're fine. So we're saying if new direction is different from the old direction, then the chain starts at 2, I guess. New chain. It can never be 1 again. It's always going to be 2. Else, new chain length equals chain length plus 1. So it can only ever be 2 or 3. Let's have a look at the diagram of their solution. So 2, 2, 3. Oh! No, this is not quite right. Hang on. No. It's a chain means how long you've been going in that direction. So chain actually means... So it starts from 1. Because the space where you just were doesn't count. Because you weren't going in that direction. So you've moved... in this new direction, if it's different, you've moved in that 1 space. So it's the chain length so far is 1. Otherwise, it's chain length plus 1. And if you have already gone 3, turn. Okay, that works. So you can, okay. Finally, just yield this new state. So it's going to be new pause, new direction. So this is the crux of the algorithm. The algorithm. This get neighbors. Everything rests on this being accurate. So I hope it is. Okay, fine. So we yield that. Okay, so back to the main method. So for neighbor state in get neighbors current state. Okay, so so we want to do the G distance, which is the shortest path. G dist. Hang on. The other thing I need to check is if we've gone out of bounds. New pause. If not, so we need to say new, so it's going to be 0 is less than or equal to new pos dot row is less than n, and 0 is less than or equal to new pos dot col is less than m. Let me skip that one. So we're not allowed to go off the grid. So if you hit the edge of a grid, you can still turn, that's fine. Alright, so for neighbor states, so these are valid neighbors on the grid. Distance is going to be basically the heat of that one cell that we've entered. So the G dist equals the dist up to the current state plus, and then we do grid pos dot so it's going to be current state pos the row and then the col, and turn it to an int. I mean, we could have made this ints. Should we do that? Yeah, let's do that. Grid.append, so it's going to be map, so it's going to be list map int to line.strip, so it's just going to map each of those characters to an int. In fact, I prefer it to be a tuple. Immutable. Okay, so we don't need the int. So that is the distance. All right, now we say if neighbor state is already in our dist table, and it just so happens that we found a better, shorter path to this neighbor state, smaller than G dist. Then we skip this because we found a better path. So no point doing this. There's no harm in adding this to the queue. It just wastes. No, there is harm. We would go around in infinite circles. Okay, so at this point, I think we know. So now we can say dist neighbor state. So the best path we've found to neighbor state is G dist. And then finally we want to now put this neighbor in the queue. Queue dot put. So we want to start with the G dist. So it's going to be dist neighbor state plus the H value of the neighbor state. And then the second parameter is going to be the neighbor state itself. Should I just make sure this all compiles? Yeah, okay. So that just, if I run this now, it would just search the whole map, but it won't find the goal because we didn't define the goal check. Goal check is done here. So the moment we see that it's the goal, so if current state 0 equals goal pos, return dist goal pos. Now the reason we can't put this line here, like we could find a neighbor, which is the goal, right? The reason we don't just output it immediately here is because that's not necessarily the shortest path. So we might find several paths to the goal, but only when we pull it out of the queue, i.e. the item with shortest priority, only then are we 100% sure that that's the shortest path to the goal. So we return the distance there. And now we run it, and I bet it's going to get stuck in an infinite loop. It's very easy to get stuck in an infinite loop with A-star, with Dijkstra or breadth first search, or well, let's see. Part 1, print A star start state goal pos. Alright, first error, int and tuple. That isn't... Oops, what happened there? Forgot to put the H. Yeah, there we go. Bad operand type for unary, none type. Yeah. Oh yeah, I forgot. The one exception. Alright, so if... Alright, so... There is no direction to begin with. So direction is none. So we can say if direction is not none, and we have to say this as well. Where else have we used direction? Yeah. Okay. Less than not supported between instances of pos and pos, of course. We have to define less than. Just return true. It doesn't matter. They can be ordered arbitrarily. Alright, less than takes one positional argument, but two are given. It's going to be other. Return true. And we're in an infinite loop, of course. So, the most probable issue is that we're not using the... What's that noise? We're not using the dist table to avoid going around in circles. Now, let's see. So we're allowed to revisit past locations. But we're not allowed to revisit past states. So if a state but we never put a state in the back in the queue if we've already found a shorter path to it. So that should prevent infinite loops. So print length of queue. I don't know. Sorry, not length. Q dot size. Q dot queue size. It's just growing and growing. Right, stop. What is the maximum size this should be? So there's one. There's how big is the grid size again? Let's get rid of that. 141 by 141. So it's gonna be one for one. Oops. One. Oh, this is not Python terminal. Python console. 141 times 141. So there's that many positions, and for each of those, we could have 4 directions. And we can have, for each of those, we can have 1, 2, or 3 length chains. So 3. 238,000. So that's the max size of the queue. So maybe I should just let it run then. Let's say we'll keep an eye on the size though. It shouldn't exceed 238,000. Otherwise we have... Oh, it could exceed it because of the lazy deletion thing, but it shouldn't go much more. Right, let's say if queue size % 1000 is 0, Just put in the queue size. I just want to see how big it's getting. So it can go up to the 200,000s. But we are clearing out locations as well, so... Now we're using A star, which should speed things up. It should try to go follow the optimal path. It'll try to prioritize routes which are kind of directly going towards the goal physically. Okay, we're reaching the 200,000s now. I don't really see it decreasing. Okay, it did decrease a bit. It's going into 300,000s. Clearly we are pulling things out of the queue. Alright, so it's kind of filling up with junk, but it's not finding the goal. Or at least it's not yet found the best path to the goal. Let's let it run a bit more, I guess. If... So we said if... Maybe I should run it on the simpler example. Because this isn't really telling us much. It might still be in an infinite loop then. What's going up and down? Oh man. Is our A star algorithm just not very good? Because it's not really that good, is it? It's we're treating everything as one. There aren't any zeros, are there? But usually it's better to do that than nothing. Now we're in the millions. No, it could be stuck in an infinite loop. Oh, we're rapidly decreasing. Ooh, ooh, ooh! What's happening? Let's watch it. I'm curious. It's not very efficient, is it? But can we do better for the A star? Because no, not really. Because you can go zigzag, zigzag, zigzag. So A star the Manhattan is kind of close. Except, of course, these numbers tend to be bigger, but you don't see many ones appear towards the end. Oh, you do. Goal pos equals pos n-1, n-1. We'll run it on the smaller example. Also, I'm curious whether we actually hit the goal. Why is it filling up so much? It shouldn't be. I mean, we can be finding smaller distances to locations, but still, it shouldn't fill up so much. This lazy deletion thing is too lazy. I think we're just finding a lot of kind of not very good paths and leaving them in the queue, but there's not much we can do about that. We can... Let's say if... So neighbor state... Alright, let's stop printing this. That's slowing it down as well. If we see the goal, neighbor state 0 is goal, pause, print goal. Alright, I want to see if it hits the goal. Even finds a route to the goal. It should. Chain length plus 1. Oh, are we exceeding 3? If direction is not none and delta equals direction and chain length equals 3, continue. No, so we can't have delta be the direction again there, so that will reset the chain length. We're not seeing the goal. Damn. Alright, let's try the example then. I think we must have an avoidable loop then. Okay, now run it on this. Key error. So we've seen the goal several times. Return. Ah, that's wrong. Okay. 101? Was that the answer? Never moves more than 3 and incurs a heat loss of only 102. We found a better path? That can't be right then. 102. The answer should be 102. How on earth did we get 101? How can we be one off on this? That doesn't make any sense. Also, when we're at the goal, we shouldn't be adding new states. So... No, but that's fine, because the moment we pull out the goal, we're done anyway. 101, we can't... How can we get... one less than the shortest? Did they actually say it was the shortest part? No, one way to minimize heat loss is this part. They haven't actually said what the shortest path is, so we probably found we could have found the shortest path. It's a bit strange that the shortest path would be 101, and they said one way is 102. I'm curious as to what the G-dist is. So we found 101, 103, 103, 103, 103. Wait. So we found 101. Okay. We put it in the dist table. Then why did we put these ones in as well? Well, because these were different states. I guess that's correct then. They were the same pause but different states. Okay. So there's only so many different ways you can end up at the goal. We do end up putting them all in. If neighbor state has been seen before, and our distance to the neighbor state is less than what was found here, we skip this one. Yeah. So we didn't find any path of 102, but I guess that's fine. So for the big input, do we ever reach the goal? Maybe we... Should I try just switching off the heuristic? Sometimes it can be bad if it's just not very good. Sometimes it can actually make it all worse, so let's try this. Our heuristic is 0. Now we're just doing plain Dijkstra. Now let's see what it looks like. I think we do want to have some sort of heuristic. Seems to fill up faster, but I suppose that's correct. No, there's something I must be missing here. I think... You know what? The first time we see the goal, that is actually guaranteed to be the shortest path, because the final distance to the goal is fixed, and it's always going to be the same wherever you approach from. It's going to be 2. If I approach from there, it's 2. Approach from there, it's 2. So the first time we see the goal was already the shortest path to that previous node. So we just add on the 2. So, slight optimization. We don't need to do this anymore. We don't need to goal check here. Just if we see a neighbor, if here we just return gdist. Okay, the moment we see the goal, we're done. Maybe that will improve things, because it was probably taking a long time to let's not print as much. Let's change this to every 5,000. Maybe 10,000 even, but just leave that running for a bit. So now I reckon we might actually see the goal, but it takes a long time before the goal actually gets pulled out as a current state. But the moment we see it, we're done. So just return gdist. Alright, let's hope. Big sizes. And that would explain why 101 was the first number we saw and was the best one, because it does actually find the best. First time, and everything that comes later is actually worse. Well, yeah, in this part. So we know 238572 is the number of states. So I still something doesn't seem right. We're getting way too many of these. There should only be... Well, I guess there's just a lot of lazy deletion. Is there a better way of doing this then? Because this is going to keep happening. So we find a path to a node, then we find a better path to that node, but the old path that's still in the queue. Then we find a better path, but the old paths are still in the queue, and so on. It just leaves lots of bad paths. I think lazy deletion is the key, but we're doing it correctly. There's no better way of doing it, so... Is this calculation correct? If fdist is bigger than dist current state plus h current state. Yeah, because that's what we would have put in. That's just too many. How can there be that many? We're in the millions now. It doesn't make sense. Yeah, Oh, it's dropping. Doesn't mean anything if it's dropping, though, does it? Whoa, whoa, it just shot up to 1 million again. It's interesting, Harry. Okay, okay, is there... What other optimizations could we do? So we know... When we're at a cell, we can go forward, can turn right, can turn left, can't go backwards. Maybe there's some shortcuts we can do. For example, we could immediately see 3 spaces ahead. So we could go 1, 2, 3. And add those nodes in. But that's not really shortcutting, is it? I think we need a better heuristic. But what could we possibly do? Was there any other... Let's have a look at the... No, I mean, you can go back, you can go forth, you can revisit nodes. Do we ever want to revisit a node? Should we ban that? I mean, what's the benefit of revisiting a node? No, but then I mean, Dijkstra should take care of that, so... We're allowed to revisit nodes, so if there's a reason to, it will become apparent, won't it? Alright, we need to look at these locations. I think something might be off. Like maybe we're going off the end of the grid or something. Return state the pause.dist goal pods. Yeah. Have we done dist correctly? Self row minus other row, self column minus other column. Yeah. We're minimizing the This is a part 1. So there must be some trick that I'm missing here. Maybe I should... Let's have a look at the state definition again. It's a pause. Equality should be defined by the tuple. Hash should be defined. Doesn't make any sense. How can it be that big? Direction, chain length. Right, I'm going to take a quick look at the Wikipedia on A*. Maybe I've missed a very important step. Maybe there's an important step to stop infinite loops or something, I don't know. Alright, so open set is, yeah, priority queue. Came from, we don't need. G score is the distance. F score is G score plus the heuristic. Alright, so current, we pick the lowest F score value. Yeah. If it's the goal, yeah, we don't actually need that. Open set dot remove current. That's the tricky one because we have to do lazy deletion. You can't really delete. I'm not sure. For each neighbor, so G score equals G score current plus the edge, which is going to be the heat. And we're trying to. Hang on, how's heat loss defined again? I don't think I even properly read that bit. The amount of heat loss is the number. Okay, yeah, that's fine. Alright, so, okay, and then this bit down here, if what we found is better than what we knew before, that's an important line. Are we doing that? Pretty much, yeah, just worded differently. If distance. I could put a less than or equal to. Ooh. That might make all the difference. Hang on. Let's see. Okay. So. Alright, so before I had this. I was saying if we found a strictly better one before, we skip this one. Okay, I'm now saying if we found something less than or equal to. So I guess maybe the problem... Okay, let's stop. Stop the process. Maybe the problem was we were adding lots of paths with the same distance, which is wasteful. We only want things which are strictly better. So that can cause infinite loops. Oh, man. Wait, okay, run it. Let's see what happens. Now we're not filling up. Boom. There we go. That was the one. That was the problem. Yeah. So we were basically adding lots of paths, which have the exact same path. So anytime we found, which also means we would keep revisiting the cell at the same place over and over again. Yeah, okay. We need to only... Yeah, okay. Want to find... Well, I don't know. Is it correct? Let's check. Fuck. It's too high. But at least it terminates. Okay, so now, see, infinite loops are the worse things to debug. Okay, we've fixed that bit. Are we sure about this? Should I go back to... this? Let's go back to this. Take this out. 1249. No, it's the same. Okay. So I think we can do that. No longer need to print the queue size. It says too high, so there's a better path we haven't found. Also, are we using the full chain length? Is this correct? If chain length is 3, then we have to turn left to right. That's right. Excuse me. New direction. So direction will only be none once. All right, try the example again. They don't give... Alright. Let's run that. 103. Fuck. What's happened? We had 101, now we've got 103. Oh? What? Alright, go back to go to this version. So we had a better path, now we're not finding the better path. Now that's correct. So apparently this logic's wrong. But that's not the problem for the large input. Alright, so why is that wrong? I'm saying if I see a neighbor... Oh, yeah, I see why that logic was wrong. Because that was the shortest path to that state, but the preceding the goal, but it was not the shortest path to the position preceding the goal. There could have been a shorter path. Okay, so yeah, just take that out. Alright, so you do have to do the goal check when you expand. And anyway, that's the textbook approach. You should be doing it here, always. Anyway. Alright, so 101, but... 1249, but if we go to the big input, we get 1249 still, so that didn't fix that issue. 249. It must be something small then, because I mean I've now got what I think is a good A-star algorithm. Maybe I'm just not implementing the get neighbors correctly, like for delta in pos1, so it's 1 0 0 1 minus 1 0 0 minus 1. You can't go backwards. And if chain length is 3, 1, 2, 3, then we can't go forwards. Is 3 the right number there though? Hang on, so 1, 2, 3, and then guess so. So from the first node, we're getting the right neighbors from the first node. We start on 5, but we don't count the 5. So we can go right or down. Yeah, those should be covered. And if we go out of bounds. Yeah. New direction equals the direction we just went. If new direction is not equal to the original direction, we have followed this direction for 1 iteration. Chain length is always going to be 1, 2, or 3. One, 2, 4, 9. It's too high, so there's a better path. What? There's an error of logic here then. So it's not about efficiency or anything. If fdist is greater than, there's a better yeah, that's right. Should we go back to using, should we just set the heuristic to be 0? Just in case this is invalid heuristic. Okay. So I was thinking maybe he's thrown in some zeros that we haven't noticed. Because that would make the heuristic inadmissible. But no, that's not the issue. How long does that take to run? And if we go back to using the heuristic, it's roughly the same. Doesn't make much difference. Try printing the dist. I want to see what the dist table looks like. This is difficult to debug now because can't really by hand. Oh no! What? 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 What is that? -1? Oh no, sorry, that's fine. It's fine if there's a 0 along with it, because that means it's a direction. I thought that was coupled with... Okay, yeah, that's fine. Those directions are allowed. I thought I saw it coupled with a... a non-zero integer, which would indicate that we've gone off the side of the grid. Alright, so these numbers look fine, I guess. How am I going to debug this then? Because I can't really work this out by hand. Why would it... We are allowed to revisit cells, aren't we? Yeah, we should be. It's just states we're not allowed to revisit. Or at least that's handled. Distance. No, I don't know. I don't see anything out of the ordinary. It looks all correct. What dials? 1221. Yeah, I mean, it's like... Yeah, those numbers sound about right if we're accumulating heat. Make sure the input's correct. So the last, this should be a 5522 in the bottom right hand corner. Yeah. I don't know where to begin debugging this then. What could be the issue? Just gotta go through the logic again. I can't do this by hand. So if we are not finding a shorter path, if there exists a shorter path and we're missing it, so one possible reason could be that we are missing out some neighbors. So are we accounting for all? So let's have a look what is allowed again. So they said it can move at most 3 blocks in a single direction before it must turn 90 degrees left or right. It also can't reverse direction. After entering each city block, it may only turn left, continue straight, or turn right. So we never go backwards. In any case. We can always turn left or right. But we can't go forward when the chain is... What happens if we set chain length equal 4? I'm just curious. I know this is wrong though. 1184. What does that do for the smaller input? $96. We don't know what the correct answer for the smaller input is. That's the annoying thing here. Oh! No, they did say one way to minimize heat loss is this path. Oh, they did say that is the minimal heat loss, is because they said one way to minimize. Hang on. So we don't have the correct answer for the small input. They did actually say that's minimal. Just the way they phrased it, it wasn't completely obvious. Oh, crap. So we are one below the correct answer. How could that possibly be the case? We add... And they said our answer was too big. What the heck? So the correct answer is 102. I guess we're just gonna have to output the actual path and see why 105. Goal pause. Oh, you know what? This goal check might not actually be correct after all. We're cutting corners here. Because we really... So we're leaving early if the pause is the goal. But there could be other states where the pause is the goal with different directions and different chain lengths. So... Is this correct? Is there a way to end early if we find the goal? I don't think so. I think even if you find... You have to think in terms of goal states and not... But... Alright, let's test that. So if I just take out the goal check. Alright. So then we just exhaust all paths, and then we can now print dist. We need to find the minimum. This is interesting. Yeah, I think this is what we have to do. We have to find the minimum. Yeah, I think we can't make this assumption, yeah. We can't just check the goal pause. We have to think in terms of states. So only when we've found paths to all goal states, of which there are many, because there could be different chain lengths and directions we arrive at the goal with. Only when we've computed all of those, then we're done, and we know that's the minimum amongst them. Okay, so we need to say we need the minimum of dist state for state in dist.keys if state.pos is goal pos. Return. What does that give us? Tuple has no attribute pos. Tuple minimum distance of a state. Oh, no. State 0. 101. Damn it. We still think we've got a better... that wouldn't have even solved that issue anyway, because... What does it change? Does it change this? No, I think this goal check was actually correct the first time, but we'll leave it out. So let's exhaust all possible paths, all cells, and then... Wait, how on earth have we found a better path for this? We have to print out the path. Yeah, we're gonna have to print out the path. Like, so they're saying the best path is 4, 1. Also, we'll take out the heuristic again. Just be as basic as possible. 101. They said the minimal solution is 102. How could I possibly be 1 over? So how could I possibly have be 1 under? How could I have found a shorter path? Am I adding in? The only place where that error could have occurred really is when we're adding the distance, surely. And we do that here, plus grid, current state 0.row. Oh, fuck. That should be neighbor state, not current state. That was the most noob error I've made so far, and it ended up being the most damning. Distance to current state plus the edge to the neighbor state. There we go, 102. We can put back in all the optimizations and it. Well, okay, let's just leave it like this for now. My god. That was stupid. 1, 2, 4, 6. I think the trap I fell into was I thought that I had the right answer for the small input because I didn't think that the problem description actually was minimizing it. I thought they were just giving an arbitrary path, but then the wording of it does actually imply it's minimal if you look minimize here. So yeah, I missed that one. So it's 1, 2, 4, 6. Surprisingly close to what I had, even though I was using. Yes, because I was always using the. Yeah, I was always one node behind. Yeah, makes sense. Alright, part 2. The crucibles of lava simply aren't enough to provide an adequate supply of lava to the machine parts factory. Instead, the elves are going to upgrade to ultra crucibles. Uh-oh. Ultra crucibles are even more difficult to steer than normal crucibles. Not only do they have trouble going in a straight line, but they also have trouble turning. Once an ultra crucible starts moving in a direction, it needs to move a minimum of 4 blocks in that direction before it can turn, or even before it can stop at the end. However, it will eventually start to get wobbly. An ultra crucible can move a maximum of 10 consecutive blocks without turning. Okay. So they're saying the cap is 10 instead of 3. And the min is 4 instead of 0. So we can parameterize our current method. To do this, so okay. Shouldn't be hard if we just 1, 2, 4, 6. Are we still using the heuristic? Let's go back to using the heuristic, make sure it actually works. Yeah. And is this allowed? Yeah. Okay. Alright, so we want to say we want 2 more parameters. So we want a min chain before turn, and we want a max chain. So for part 1, we want min chain before turn is 0, max chain is 3. So let's just put those in. So this all comes under get neighbors. Max chain. Alright, so the only difference now is we have to min chain before turn. So if the chain length is less than min chain before turn, then we don't turn left or right. if direction is not none and delta not in minus direction, that means this is a left or right turn, and chain length is less than min chain before turn. Then we continue. That's it, right? Now we have to make sure this still gives us the same answer. 1, 2, 4, 6. One, two, four, six. All right. So part 2 will just be so what was it? They're saying you have to have a chain of at least 4 before you can turn. And the max chain is 10. Is this going to take much longer? Because, yeah, now... So you could skip ahead. You can just not do the 1, 2, and 3 chains, because you know that... Alright, we'll see if this is the right answer. Because you know those have only one neighbor. Yeah, that's right. Yeah, I mean, you just parameterize it for part 2. Part 1 was the tricky one. So yeah, you could... It doesn't save much time though, but you could basically omit the one chain, 2 chain, the chain 1, chain 2, and chain 3 nodes, because you know they will only lead in sequence to the going forward step. So you could just kind of look ahead, start from 4, and from 4 up to 10, you put a node for each of those where you're allowed to turn and have to turn. So basically, the neighbor nodes from a cell would be the left turn at 4, the left turn at 5, the left turn at 6, so on, and the right turn at 4, the right turn at 5, the right turn at 6, and so on. Then you'll not bother with all the nodes in between. It probably wouldn't. It might create some overhead though, so it probably wouldn't be that much of an optimization. All right. So yeah, this is the thing about A star. You know, you write it from memory every time, and I always end up getting either an infinite loop to start with, and then maybe some logical error or something. That's just how it goes when you write Dijkstra. It's not an easy algorithm to write, even though it's it's like, I mean, I studied Dijkstra at school. We actually, at school, in mathematics, secondary school, we were given questions where it was like a bunch of nodes connected with edges, and you actually had to run Dijkstra's algorithm on it with pen and paper. So conceptually, it's not a hard algorithm to understand. It's just you got to use the data structures correctly if you want to be efficient. You could not, if you don't want to use a priority queue, you could just use a list or something, but then you're using linear time every time you find the minimum. Or you could use a binary search tree. Oh, no, that wouldn't be good. That would be more work than using a priority queue. Yeah, lazy deletion was fine. It was accumulating nodes because I wasn't correctly checking whether we've beaten our previous best paths. So we're just adding lots of paths. The same paths over and over again. So yeah, that was an infinite loop. Alright, well at least it's a nice easy part 2. I mean, where else could you go from there? Well, he could have come up with more complex things for part 2. Alright, is this in a state that I want to paste it into GIST? Yeah, I guess so. Alright then, we are done. Let's just take a look at the... So we're still on... 18 will still be on Gear Island, I guess? Judging from this, I'm not sure. 17. 5 minutes 03, bloody hell. Well, yeah, I mean, if you just paste in your A-star algorithm that you have pre-prepared, this, which is made generic and handles goal states and everything, then yeah. All you literally have to do is define the state. And you don't even need to throw in a heuristic because it doesn't seem to have much of a speed up. So yeah, just use Dijkstra. Even I could have done it. Well, if I had a working Dijkstra code, then I could have done it pretty quickly. All right, and then let's just check other things for private leaderboards. Okay, Sam has done one. Umaro might like this one because, I mean, this comes up in game dev and would be handled by game engines. I mean, a lot of game engines have their own pathfinding stuff built in. But they're normally assuming physical distance or number of tiles. In this case, we're thinking about heat loss, so I don't know if there'll be a generic enough methods for that, but anyway. And on Captain Coda's leaderboard, oh wow, I'm one of only 2 that have finished it so far. Interesting. Or Alka. We raided yesterday. Alright. Nothing more. I need to go back to sleep. I'm still pretty tired. That was a nice problem. It was very textbooky. You know, you could get that in a classic computer science algorithms course, have that on your final exam, and be expected to write working pseudocode, you know, within 5-10 minutes or so, because you got a bunch of other questions on the exam. So, you know, that's every computer science graduate is expected to be able to do that, and way faster than I did. I took 2 hours. It's not unreasonable to have to write Dijkstra in a matter of minutes, so I gotta get better. You can only get better by forcing yourself to write A-star from scratch every time. It just... That's better than copying and pasting it in. It's just annoying that I keep running into errors, but you learn from them. Infinite loops. You've always got to make sure you're doing the open set checking, the closed set checking correctly, to make sure you're not revisiting nodes. Or just visiting nodes off of rubbish distances. Alright, see you tomorrow for problem 18. Bye bye.